Well, welcome everyone to the, oh my goodness, October meeting of the Seattle Robotics Society. Oh man, I can't believe how fast this year is flying by. Just seemed like I just did the January 2022, what, a month or two ago, right? That's what it feels like. Anyway, welcome everybody. Glad you could be with us, and welcome Bill. It's been a long time since we've seen you. So always glad to have folks dropping in. I see Randy and Lloyd and Bob and Dick. And let's see who else we got here. Yeah, Bill, John, Chaz, Mitch, Nicholas, our presenter there, is hanging with us. Welcome. All right. Okay, let me just start. Whoops. Did I do that? Did I do what I wanted to do there? Yeah, here we go. Okay, so we're going to follow the usual agenda, which we'll hopefully catch up on the screen here in a moment. Sorry about that. Zoom can be kind of slow and pokey sometimes when it comes to, boy, sometimes it's just really painful. It seems like it's in mornings for some reason or another. It seems like Zoom is slower than in the later in the day. I don't know if that's a real thing or what. Well, anyway, I'll go ahead and just kind of start. I'll start just talking through the slides here. It will eventually catch up, I'm pretty sure. So we'll just follow our usual agenda. We'll do some club business, some just kind of general comments and discussion. Talk briefly about future presentations. We'll talk about, hopefully hear from the Robothon committee, hear a little bit about what's coming there. Yeah. We'll do some round the web demonstrations and announcements, and hopefully you guys have some things to show. I don't actually have anything in particular with this little robot here that's got my name attached to it. It's just gave me something to do with that camera, so I've just got that thing sitting there. And then we'll take a short break, 5 to 10 minutes or so, and then we will have our feature presentation. And then we'll conclude, and we'll have a after-meeting discussion that can continue, but that's usually unrecorded. So, boy, that is really okay. Let me try this again here. I'm gonna share. Maybe I'll try it this way. No. Let's see. Oh, get rid of that. It's not the one I want. That's the one I want. Okay. Sorry about the technical Zoom issues here. Good grief. No, come on. Huh. It's interesting. It's seems to be mostly having issues just with actually sharing the screen. It's like the camera feeds come up right away, but other stuff, there it comes. Good grief. Okay, so I talked about that. Oops. Oh, that's weird. Why does it keep doing that?
You gotta mute the mic on the video on that side. You've got your video, you've got your audio muted, Steve, and you've got the bot is the one that's picking up your voice, and so every time you talk, it switches to the bot video.
Let's see. Yeah, let's see here.
Yeah. You're gonna have to shut off the speaker, I guess, on that other one, or maybe it'll be okay now. It seems like it's
yeah, still doing something. Yeah, I still got something wonky happening here.
Usually that happens when the sound is
Think what we
coming
need.
out of the one that you wanted muted.
Okay.
So I don't know if you can turn off the sound on the robot one. Or we'll just have it switch to the robot every time you talk, Steve. Who cares?
Okay, I think. All right, I think I've got. All right, so let's see. Everybody can hear me okay? Give me a thumbs up out there somewhere. Okay, thank you. All right. Let's see. Pardon all of my Zoom issues. If you guys, anybody out there is not muted, it sounds like you all are, so that's good. So just go ahead and do that and unmute if you have something to share. Otherwise, just stay muted. That'll hopefully keep the camera from doing some wonky things. In-person meetings. We may chat a little bit more about this come, as we move forward. I'm actually moving to Idaho, and so I will not be available to run in-person meetings. But we are still planning on doing that at some point in the future. I reached out to Kevin Ross and have not heard back from him about the First Washington facility down in Kent, the new one. So I don't know. Whether or not there's a place available, but there will definitely be a need for assistance in running the in-person meetings and also possibly alternate meeting leaders from time to time. So, reach out to us at the Seattle Robotics Society email and let us know if you can help with that. We would really appreciate it. Yeah, okay, so mention that. And so Lloyd's going to be kind of step in as the local guy for the moment, but he would love to have as much assistance as is available. So keep that in mind. Just a quick mention, I am teaching middle school children ages 10 to 13 hands-on robotics via Zoom. So anybody who knows kids in that age range who might be interested in that can email me at this Mr.Stevesroboticsclub@gmail, and I will send them more information and would love to chat with them. I do have you can also friend me on Facebook. My name is on Facebook is Stephen Kaehler. So I will be happy to pass along information. National Drive Electric Week. I did another one of these events up in Snohomish. Great fun, nice turnout. Highly recommend those things if you're into EVs. And let's see, and then it's just some other events going. I have another slide about the Snowco Makerspace, and there's some other folks online here who can say more about that, so I will let them kind of provide some more details. Let's see. Public exhibition. Maybe I'll let. I saw Lloyd was on there. Lloyd, you want to jump in and I don't know if you have anything really to report regarding the actual public event coming in 2023.
Yeah. So what we're talking about for 2023 is trying to do a Robo Magellan run. We may be able to do this. We're looking into possibly doing this at Seattle Center. In concert with one of the war events. If we do that, it'll be back on the mural lawn where we normally are, if that's available. If we don't do that, we'll probably do it sometime later in the year. And there's a number of schools and other places we can actually do that. So I think plan of record is to try and do a Robo Magellan run this year. We may also do a PopCAD run. We're kind of seeing how that comes together. And of course, we'll probably continue doing our online events of the Robothon exhibition. Those are going really well, actually. We've had good participation. We've done 3 of them now, and every single one has grown with both number of participants and number of speakers. So no matter what, we'll keep doing those into the future as well. So we'll keep you posted. probably be around the first of the year when we know exactly what we're doing. But that's our plan for 2023.
Okay, thank you, Lloyd. All right, I saw, let me see if it comes back up again here. I got a slide. I have a slide about the SRS PopCan challenge, and I saw Chaz on the line there, and I was going to see if he would mind jumping in. You can go ahead and unmute and tell us a little bit about what's going on.
Yeah, so we're still on track for, can you guys hear me okay? Yeah.
Mm-hmm.
Yeah, okay, good. So we're still on for November 5th. We're actually in the works. Well, actually, I can't say we, Greg has done all the legwork on moving this to Third Place Commons in Lake Forest Park. We'll update the meetup, we'll update the Sunoco Makerspace invite, we'll update the PopCan Challenge Facebook group, all of those areas that we posted on if that happens. The only reason we are looking to move there is just because they have more room, and there's a bunch of tables, a bunch of seating. It's free. I mean, the makerspace is free too, but and there's places to eat, so it's kind of just a better place for people to come and look at it. And it's like a big, well, it's a commons, right? It's like a big open space, and they have a whole bunch of food around it. And it's a little bit nicer for the people down south because it's in Lake Forest Park, so it's just north of shore. Well, I guess east of shoreline, right at the top of Lake Washington. So we're looking at doing that. We also have right now we're talking to the war folks, and the date is just, I mean, I'll give you guys an update on it later, but the war folks are doing a May 6th and 7th in 2023, and they want us to run the PopCan challenge there as well, and we're likely to do that as well. So we'll have another one in a couple months in May, and at this, I don't know which building yet or anything, but the war folks, you know, the robot war guys are looking to have us there as well. So that's what's going on with us.
Cool. All right, thank you.
Yeah, thank you.
Yeah. Right. Oops. And let's see. Online presenters. Of course, I'm always interested, and sent out about a dozen invitations here a couple of days ago. And Robert Kellogg has been really good about pumping me with plenty of suggestions. Today's presenter was one of his suggestions, and so I'm very pleased to have him. We're always looking for folks to talk to us in the second half of our meeting, so that will be happening a little bit later. If you have suggestions or you run across people that you think would be interesting, just send an email to me at the Seattle Robotics Society at Gmail, and I will follow up with them. Let's see. So I'm kind of getting. I've been sort of remiss in staying on top of this. As you can see, January, starting in January, is like, oh, we got all these open slots there, so I got to really get going on this. But we have. I hope, I don't know if I'm pronouncing this correctly. Dr. Nadeau, is that correct, Nicholas?
Nadeau.
Nadeau. Okay, Nadeau. So he will be talking to us a little bit later, and he is going to be coming up today, and then we'll be having a couple of other interesting, hopefully it's an interesting facilitated discussion in December that I will be hosting. So be here for that. And then these are just kind of possible topics. I mean, if anybody would like to lead a facilitated discussion about something in particular that maybe they're interested in or have a little bit of a passion for or whatever, that I would be more than happy to set you up to do that. We'd love to have there's always lots of interesting things to talk about. So, and we've had some really fun chats in the past, so we'd love to do some more of that. And this is just a little slideshow I put together. I don't know how much Dr. Nadeau is going to talk to us about this particular robot. Primarily, we reached out to him regarding Pybotics, but he is also a Chief Technology Officer at Halodi Robotics, if I'm pronouncing that correctly. And we hopefully will maybe hear a little bit about some of that too, because this looks like really cool stuff. So stay tuned for that coming up after the break. And then, of course, following the formal meeting, then we will just continue having just general discussion. You can just, I turn off the recording, but you can just go ahead and, share, talk, kind of the post-meeting mingling that we were accustomed to, but doing it online. And so with that, I'm going to go ahead and kind of open the floor for you guys. And I know several of you have some things to share. So I am going to hand it to whoever would like to do that. I know Bill Harrison is here, and he's got some robots to share as he always did at SRS meetings. So you want to lead it off, Bill?
Sure.
All right. Oh, I remember those.
Yeah, these are genuinely antiques, like Model Ts. Both of these, I just grabbed a couple on my way down. This is my wife's computer. She set me up. I'll have to figure out how to set it all up on my computer next. But that's why I probably have a label of Tatiana. That's my wife. At any rate, this is Johnny Walker 1, which I feel is my most weird, but everybody else says innovative robot I've made. This one was, forgot the name of this one, but it's the idea of having a little dome and, wheels, and this thing runs around with whatever sensors. And I have several of these that do different things. This one's not operational at the moment. I think this one is operational. Let's see if it goes.
The
So
one
John,
on the left
is it?
looks a bit like it's conjured together parts from the old MIT Rug Warrior.
Okay, so and it does crash. Let's put it over here, move this over here. But I wanted to get into walkers, and so I came up with this Johnny Walker 1. This is it's not the exact original one, but it's a copy of the original one, because I don't know what happened to the original one. My hypothesis, somebody thought it was a toy and took it home or something.
Could you pull that a little bit closer to you, Bill? There, you're just kind of off the bottom of the screen. Just the other way. I'm sorry. Pull your table. Pull that back towards you. The tabletop there.
Yeah. Let me get a box or something. Hang on.
Okay. So what was really cool about that robot was that he was able to create a walking robot with a single servo, because I don't think anybody had ever seen anybody do anything like that before. That was what was so wonderful about that Johnny Walker. Oh, there we go. Yeah, that'll help. Okay, now pull it toward your edge of the table, of the board there. There you go. Yeah, there we go. Now we can, because now we can see the whole thing as it's moving. All right. Can you make it go again for us? Oh, you're mute. You got muted somehow.
So can you hear if I talk now?
Yes, we can.
Okay, as long as I hold my finger on this button, apparently you can hear me. So what button on the keyboard do you hit to keep being heard?
Does
You have
anybody
to
know
click
right
the
off?
mute. You have to click the mute symbol with the mouse.
So,
Oh, there's a mouse.
Should be on the bottom.
This is my wife's.
yeah.
Did that work?
Yes,
We're
it
hearing
did.
you.
Oh, let me. Oh
Yeah,
no,
works.
that's what we that's what we want. Yeah. Okay. So at any rate, the masochist that I was, I take on things and people say that's absolutely ridiculous. And that's just the kind of project I want to do. And the Johnny Walker one was one of those. And I spent, and a lot of people call it wasted, an entire year coming up with this. I have a pile of pieces and parts. You know, there's nothing to go by. So basically I tried building something, didn't work, tried building something else, didn't work. Sometimes it was a whole design, let's start over. And you get to the point finally where you have to refine it. It's very tricky to get it to balance just right. So this is my other robot here. This one you just have to give food to, and it is automatic.
Ah.
Can you take down? Can you take down the dome one and have the other one walk for us again? Just a little walking.
Yeah.
Just like that.
Yeah.
Or do you want? Or do you want? How about a little bit of an angle?
Okay.
And what it does is it swings the battery. There it goes, and the feet are like this. So if it pops up in one foot goes out off the floor. If it pops up on the other, and the tape is obviously old tape. Wonder why. Let's see if that works. And it's just a standard airplane, you know, flap, model airplane flap servo, not modified at all. And it's got a basic stamp right here. And I was really impressed with Parallax coming out with that, because when it first came out with that, that's like, really? They got it down to teeny weeny like that, and you can use it. And so this was my project to kind of take advantage of that. And then I drilled the holes in there that were not necessary, but I thought made it look kind of cooler, kind of thing. And it sounds really simple because it's just got a servo. It's got an IR receiver like a TV set has, and on each side it has a little LED, IR LED, which you can't see, but it can tell when something's there. Like I'll put my hand there, and it should go, oh yeah, look, it goes into pivot mode instead of going walking. And the way it does that is each foot has only one high friction pad, like the balls of the foot. And what it does is it does that little twisty motion with both of them on the ground, which effectively makes it twist around. You can test that out yourself. Just put your feet side by side, put the weight on the balls of your feet, and then push your legs, and you'll see the top of you is going to start twisting one way or the other. And yes, these things have fallen off tables before.
That is intensely cool. I absolutely love that.
I have a black thing in front of my, oh, I can get rid of that. Let's see, where's the mouse? Let's see, let's get rid of, oh, it did on its own before I found the mouse. Yeah, and it's a 6-volt system. And so I had this idea of, I wonder if it has a, you know, usually you design things with a little plus. I wonder if a 9-volt battery would work, because, you know, 4 AAs on there would be a little heavy for it. You know, so it went through a whole lot of things. It has, you know, it has friction feet, 2 of them with friction, but they don't both stay on the floor at the same time. It has to tip before it has friction on the other side, which gives it stability with, you know, 3-point stability all the time, kind of thing. And if it sits in the middle, it's got 4, 2 on this one and 2 on that one. So it has stability there. So a lot of this was stability, but not just the standing there. It had to have the right stability while it moved, you know, when it tilted back and forth. So you could see this is hit and miss engineering. You know, I am an engineer, but I didn't actually design this officially. I just was tinkering around in my garage and my milling machine, which at that time, it's now CNC, but at that time it wasn't. I had to hand crank, cut all these parts, and, you know, I had a lathe I could do some of the parts on, and also by hand. And so this was an insane project. However, However, it has the perk that I've had a lot of people try to copy it, and maybe they kept it a secret, but I haven't seen anybody else do this, even knowing that I did this, even looking at it. So it's not as simple as one would think.
What
Is
is
there
the
a web
function
page
of the
somewhere,
nickel?
or are the designs
Then-
available? Are you publishing this somewhere?
This would drive people crazy because knowing the design is not all you need to know. There's subtleties of exactly how long you cut it off, and the frictions. Like this has got a spring clutch setup in there so that the leg will stay where it goes to. You put there, it doesn't just flop down. So it has friction inside the top of this leg. It's just little subtleties that can drive one crazy, actually. However, there's the good news. Once you finally get it working, it's the neatest feeling in the world. And I made two, but the original one walked away from me at the Seattle Center at one time. I don't know if a kid got it or somebody outright stole it. I think most people wouldn't do that kind of thing, stealing, but a kid might have found it, and a parent might not have known what to do with it, like set it on the sidewalk because that's not yours, Fortunately, I lost two of the first ones. One of them I have no idea what happened to. Didn't make any drawings, had to reinvent the whole thing from scratch. So this time I didn't want to make a drawing. So what I did is I made two. So, and this is actually still the first one. I have another one. So if somebody tries to steal this, I have a way of recreating it because the other one, the rule is it does not leave the house. This one I can take. This one I can take with me. Yeah, I make a lot of rules for myself. So,
all right.
And I don't know if you can see the pins on the bottom, but that's what makes it go. Each foot, all it has is an L-shaped piece of plastic on there that's only attached to the foot. And the pins, I don't know if this shows up very well, but the pins are what make it walk. See, the pins push the feet. And that's why we needed the friction in the thing so that it would push the foot and then keep it there and then move on. And it can do slight inclines, but it's not designed for any kind of tilting or rough material or anything like that. But yeah, it was quite an interesting project. I am slowly, and since you remember when this was built, slow is really an understatement, working on a Johnny Walker 2, so it's going to have 2 servos. And on that, I wanted to do something a little different. And of course, I'm a total masochist. So one servo would control a foot moving forward and backwards, and the other one would do the lifting up and down. And you think, oh, that makes sense, until you start realizing you still have to deal with all the balance and how do you do the turns and all this stuff again. But yeah, I'll fiddle around with it. So any questions?
Okay.
Can we get a close up of the top with the board and wires there?
Oh.
That's pretty tight.
Yeah. Huh. Very cool.
Yeah, thanks for sharing.
Yeah, thanks, Bill. Yeah, that's a blast from the past, that's for sure. Well, I'm guessing that Greg, you got an update on Gidget?
Yeah, so I'm not sure if I demonstrated last time. I won't take everybody's time to demonstrate this time. I'm going to put into the chat a link to my few videos on YouTube. So if you want to, there is a video there of Gidget locating the can reaching out and grabbing the can, and then I move the can, and it repeats that process. I recently, as you can see by my backdrop, I recently put some vinyl stickers on Gidget and her trailer to kind of add a little branding there. And to further that branding, I've got the Gidget Pit Crew t-shirt. So
Nice.
on November 5th, I may not successfully get the can out of the refrigerator, but I'm going to look good failing. In terms of progress, I feel confident that Gidget can, as I said, locate the can and grab the can and carry the can. Obviously, that's not going to accomplish the task if she can't find the refrigerator and get the door open. So that's what I'm currently working on. I believe I've got the code done for, or close to done, for identifying the refrigerator. And I'm currently working on code to navigate to the refrigerator, and then I will work on getting the door open.
Cool.
So,
Thank you.
Stands.
Thanks for the update. So James, it looks like you have something you'd like to share.
Well, it's the same time, so none of you guys up in Seattle are going to go to it. But if there's anybody else silly like me who likes to hang out with y'all from California, I don't know. I thought maybe I'd started a trend and somebody else from California might be hanging out with you. There's this great event in Hackaday the same week, or in Pasadena the same weekend, called Hackaday, and this little board that they have is just so cool. I wanted to just share a couple of pictures of it and kind of show you what it is. It isn't a robot, and I'm sorry about that, but it is it's a retro computer with a front panel that you can actually program, and it's a 4-bit computer. You can see this is the ALU right here, so you have your OR output with these LEDs, and then there's AND here, and you can see the silk screen actually shows like what the function is and everything. The opcode that's being executed is decoded on these LEDs and these LEDs and these LEDs. Basically, the opcodes are 12 bits, so 3 sets of 4. The first set of 4 is the opcode. If that opcode is 0, then the second operand is this set. Otherwise, this is the X value, which would then be, like the operand Y, which would be one of these. So 10 registers, an output and input. There's a JSR, and then the program counter can actually be directly addressed. And then there's data memory. I think there's I don't remember. I'll get to the specs in a second, but the point is that you can see the data memory. So you have a little quote video screen here that you can program, and again you can program the whole thing through the front panel. So this by the way is the badge. This is the badge that you get for going to the conference, and it's all open source. This is the page for it. They have right now a manual and the description of everything, and then there's some hardware. He will, after the show, he'll open source all of the design files and the board files and stuff like that. If it's popular enough, you can actually get one. So total of 31 instructions. It's actually a PIC that's running on the back of the board that's simulating this little 4-bit processor. And it'll run from a single step, and then you can go up to one instruction every 2 seconds, and then all the way up to 30,000 instructions a second. There's 4K of programs, 256 nibbles, so 128 bytes, a 5 deep subroutine stack, and you can save and load programs via an external USB adapter. There's already assembler that's been written for it, so you can write little assembly programs on your PC and then load them into your badge and have it showing, you know, pictures and patterns and all kinds of stuff. Just, you know, as an old hacker who have actually owned a front panel programmable with switches machine, an old S100 knockoff. I mean, this just makes my heart just soar. I just absolutely love it. And I know it's not a robot, and I'm sorry, but I had to show it to you. A couple of other pictures. There's the back. You can see the pick, and it runs off a couple of batteries. There's some, you know, information about it on the back. If it doesn't work, try harder. If it still doesn't work, go to number 1. That's the program. There's an I/O expansion bus up on the top, and they're building a thing to do hardware expansion. A bunch of people have already sort of started on some hardware expansion. I think there might be a picture. I don't know. No. I think
James,
there's a picture of the hardware expansion board. Yeah, go ahead.
it's sort of reminiscent in a way of the old Alistair.
Yeah,
Where it's lit up
exactly.
from the front, that's what it reminded me. I was playing with the Alistair.
Right, all of those like front panel type, you know, with switches kind of machines. So anyway, I just thought it was absolutely beautiful, and I wanted to share that, even though it's sadly not a robot. I'm trying to figure out how to find the time to hook a couple of servos up to it, and that's why I was asking about that walking machine. It's too complicated for me to build, but if I could, I'd make my badge walk with a single servo. You know. I think everybody at the show would really love that.
They would. Well, thank you for sharing that, James. And if it's cool technology, we want to hear about it. So don't feel like if it's not a robot, we can't talk about it in an SRS meeting. You know, we're a little bit more open-minded than that. You know, it's got to at least have legs. No, it's just.
Well, I figure anything that's a computer, right? It's potentially a brain for a robot. So you know,
Right.
it's a robot component.
I cut out for a sec there. Does it have outputs that you could set stuff up to?
Yeah, absolutely.
Oh,
there
awesome.
is an output bus, and they're supposedly making a breadboard board for it. So you'll be able to like have like a what do they, in the same shape as a solderless breadboard, but it's you know, a PCB, right? You know, like those little things that Adafruit sells that are like you breadboard it first and then you solder it onto that. It'll be like that, so you can, you know, have the same kind of layout like a solderless breadboard. So I'm gonna see whether or not I can hook a servo up to it and get it to, you know, actually move something, and then have my badge wave at people or something stupid like that. Unless somebody has a better idea. If somebody has a great idea for a robot, I don't think I can power more than like 2 small servos, but maybe I can do something.
OLED on it and have it say "Hello World."
Yeah, well, it's got a little LED screen on there, so I can definitely do Hello World on the LED panel. Yeah.
James,
Hook
did
it
you
up to
listen
a
to
little
the
water
last?
blaster.
Did you listen
Oh
to the
yeah,
last Hackaday
people come and look
podcast?
at it and they get squirted in the face.
Mine only has 1 servo.
Yeah, but it's you don't have the design published, and it's hard to build, and I won't have time. But
I did publish it in a magazine a long time ago.
oh, well, I'll have to try to track down an issue or something. Anyway, that's why I was looking at it. So cool. That's why I asked about the design, because I was like, well, that's what I want to do. I want to make a 1 servo walking SuperCon badge.
Yeah.
So far, everybody that's given it a try got nowhere near and all frustrated and gave up and got mad at me. This is for advanced people only, or
Yes.
masochists.
If you make PL files for the parts, us 3D printers could knock them off.
Yeah.
What you're saying is I could sell a design.
Yes.
I would say
approach.
In the chat there was a question from Professor Nadeau, but to Greg about the door opening. And I'll let Greg answer. I actually know the answer to that question myself, but I'll let Greg talk about answer that. Is he there?
So yeah, I had to find the question. The approach that I'm planning to take, and obviously I haven't confirmed it's going to work yet, maybe this weekend, is on the gripper. So the arm goes in the gap, kind of right where the Gidget label is. There's a gap there. That's where the arm goes. On the end of the arm is a gripper, and which looks like this. And on the gripper, if it's going to let you see it, there's this little tab. And the plan is and the arm has the ability to rotate the gripper. So it's going to rotate the gripper and essentially slide that tab down the side of the refrigerator with a little bit of force until it drops in to the gap where the seal is, and then just pull back. Some of the robots in the past have had trouble opening the door because of that. It takes a certain amount of oomph to break the seal on the door, and some of the robots haven't had enough friction between the robot and the ground to do that. Gidget with batteries is about 32 pounds. So I don't think that's going to be an issue.
Very cool.
Does anybody have actual measurement of how much poundage it's going to take to pull the door open?
I mean, that's a good question. I could get that. I mean, I have a refrigerator here, and the one I think we'll be using for the contest in November. So I can get that in a couple minutes. I'll put it in the chat.
Okay, because my robot's nowhere near as big as Gidget. So I have to figure out how to get it to hold still strong enough to pull that door open.
I imagine every refrigerator has a different amount of force it would need too.
Oh, yeah, well, I'm going just for that one refrigerator.
And it's a mini fridge too, I mean, I've got a fridge in my garage that, when you first close the door, there's a vacuum that activates, and it takes a lot of force for about 60 seconds. And then finally and then it relaxes. But, a mini fridge, I couldn't imagine it'd be more than maybe a pound or two, something like that. That doesn't seem like it would be a whole lot, but
to hold it closed.
Yeah, some of them have magnets to pull the door closed, so there's magnets behind the seal. So, depending on how that's being done.
I think if your robot doesn't have a lot of mass, you're going to need to have something like the jaws of life on it, where you pry the thing open. It'd be like the jaws of life, but on a robot and like for a fridge.
So you put suction cups on the refrigerator.
Yeah, there you go.
Exactly.
Well, yeah, but it's sort of like trying to open something underwater. You don't have anything to brace against. So if your robot is too light, it's got to have a way to brace to pull, depending on how much it has to pull. Mine might be heavy enough to just pull it because it's got a real strong arm on it.
So
Maybe if
let me just say, using a digital luggage scale, for what it's worth, I was able to just now break the seal on the door with about 2.5 pounds.
Okay, that's actually kind of heavy.
And maybe if
that
someone's got
refrigerator that's going to be in the contest.
I mean, I think our plan is to use the fridge that I have here in November.
Okay. So I should look to try to pull at least 3 pounds.
Yeah.
Yeah, maybe if you get something kind of slides in like Greg's little thing there, but then pull it at an angle to get like a lever arm, you could reduce that a bit.
Well, and you know, the mini fridge, it doesn't really have a handle on the front. It's got that pocket on the top that you can pull on. It's one that opens where it opens on the left, the hinge is on the right. So, you know, my thought, of course, was if you go down the left-hand side, you're getting the greatest leverage as opposed to, say, going underneath it, but doing so in the middle of the fridge seems like it would take more force than, it seems like the least amount of force would be grabbing it on the far side from the hinge.
Well, I'm using Ross, so I can make the robot pull on anything that I can make it see.
Right. So it seems, I guess the question is, what's stronger, the arm or the drive traction?
The arm, it's mechanism wheels on it.
Yeah, so that could be the weak link, as they say.
But that can be changed.
Okay, I think John Jennings wanted to share a little bit about his Pop Can Challenge robot. Go ahead, John.
Hi guys. Yeah, let me bring up my screen here.
That's a really awesome high-tech background you have there.
Oh, yeah. So can you guys see a screen there with my?
Yes.
Okay, good. So I thought I would share a little bit what I've been doing recently. It was navigating and retrieving a pop can, but I got this little 3-minute clip of it actually opening and closing the door. So we started here.
The perfect video for the perfect time.
So one major problem I discovered at the last practice session was it had really bad traction on the concrete floor. So I ended up moving the wheels to the back end of the robot underneath that elevator, and along with changing some of the wheels and the caster. And unfortunately, that screwed up my plan on how to open the door. Door open. Now that the wheels are at the other end of the robot, I wouldn't be able to maintain that position on the door. So, so what I ended up doing was using a program that comes with Ross called, let's see, what's it called again? Ross bag files. And Ross bag files are just basically recordings of messages on the topic you choose, and then you can play back that message. And so what you're going to see in a second here, after it gets the door cracked open. Okay, so now it's going to use that. I'm going to play back a message that I recorded, and it's just me using a remote control to open the door. So I'm actually just using a handheld remote. And move back in front of the pops. I forgot to put the pop can button there, so I had to put it back in there. And then once it's in front of the door, so now I'm skipping ahead, so so you can see it actually closing the door. In which case I'm using the same type of process. It's playing back a bag file that that I recorded where it's actually just closing the door.
Well, that certainly answers a question for me, John. If a TurtleBot, because I have one, so I know what it can and can't do. If a TurtleBot can pull the door open, my other one's definitely going to do it.
But John, is that using your your Jaws of Life door opener?
Yes.
Yeah.
Can you
So-
explain exactly what that is?
Oh, it's just a linear, it's just a homemade linear servo that, or actuator, and it's reaching in and it's getting in that gap between the door and the refrigerator, and it's pulling that open with a little hobby servo. That's it's just turning a screw to spread that open.
While pushing against the frame. So
Yes.
he's not using the drive motors to break the seal.
Correct.
Gotcha.
And
size actuator you had to use, or what size servo?
I'm sorry?
Oh, what size actuator or servo? What was its
Oh, it's just a little tiny hobby servo. Because it's just turning a very fine threaded screw to open it up. So it didn't need a lot of, so it creates a lot of torque just by turning that screw.
Okay, because I have several other actuators that I could probably do the same thing with.
Is it a continuous servo, or were you able to achieve that in?
Oh no, it's a continuous rotation servo.
Yeah. Okay. So it seems to me that, I mean, that's an elegant solution. It seems to me that one of the biggest challenges is making it slim enough to fit under the door.
Yes.
That's why
and you have to have a door that actually has that little bit of a 1/4 inch lip there to get into. So this refrigerator here is actually the actual official one for the PopCan challenge. But if it's a different one, that might be so it's kind of made for this one. So I posted a link. You could see the whole clip if you want. I posted a link to RoboCame's webpage there.
So if we're not sure which refrigerator is going to be there, you could do that same thing from the side of the door too. Wedge it in the side that opens and do the same thing. That way you'd be able to do it to any refrigerator.
I had thought about that. Yeah. It does require a little more getting precise navigation. Here I can be a few centimeters either way, and I can get the right. I can still open it.
Mm-hmm. Yeah, good point.
Are you using Noetic, John?
I don't know what that is. So
Ross Noetic.
Oh, Ross Noetic. No. Yes. Yeah.
Okay, so am I. So maybe. Ross is hard.
Yeah. Hey, John, there was a question about your LiDAR sensor. Can you post something in the chat about that?
Yes, it is an RP LiDAR. And it's not the original one that came with Turtlebot. That one kind of wore out on me. So it's a different one. But it still works. It actually, I think it works better. I get a lot better resolution with this one.
Cool. Okay.
In about 2 minutes, I'll have something I can show people. If I can find it.
Yeah, if you could. We're gonna, so I want to get our mid-meeting break here. I need to go and do what I usually do during the break, and maybe some of you do as well, and then we get our presenter going. So one more thing, one more presentation, and then we'll do that. Let's see here. Huh. You got it. Yeah. See if you just.
Oh, are
There
you
you
waiting
go.
for me?
We are. Yeah. Are you?
Oh, no, don't wait for me. I'll pop in sometime. I've got to find
Okay.
it first.
Okay. Okay.
One of my drawers around here.
All right. Let's see. Is there anybody else that's got something really quick here before we take our break? Okay. All right. So let's see. So I have got about 10:58. I would say let's make it about let's make it 11:05. So let's make about 7 minutes or so. And so 11:05, everybody back here. And you guys can all go grab a cup or something, and I will I'll get our presenter. Let's see, where'd he go? He disappeared.
I found it.
Oh, you ready?
Yeah, I don't have it set up to demonstrate, but you guys might think it's just something to think about for smaller robots.
Okay, just go ahead and show it. You can show it then.
Yeah, it's a fully functioning LiDAR. Look at the size of it.
Hmm.
Wow.
And here's the hookups that go with it. For
Hmm.
putting on your board.
What do those cost? You know?
$99.
Okay.
Yeah.
Okay.
Engine.
Okay.
So I thought I bought a couple, so I'm going to experiment on real small robots, setting them up to do AI and ROS.
Mm-hmm.
That was
okay. Let me see here. All right. Okay. All right. I'm going to remove that. Okay. So, Professor Nadeau, if you could just go ahead and get your presentation, your feature slide up there, and share with us, and we can just leave that up until we're ready to go here in about 5 minutes.
You see
Okay.
everything?
We can. All right.
Good?
So, looks good. All right.
Wonderful.
So we'll be back in about 5. Thank you so much for coming and
No problem.
presenting
This is
to us.
exciting.
We are looking forward to what you have to share.
And any opportunity to chat about robots is a good opportunity.
Is this one of those organic looking arms?
So this one in the background is the KUKA LBR. They're the first cobot from KUKA. That costed way too much money back in the day for what it did, but it's a lot of fun to program. It's also their first foray into using not the traditional, what was it, the KRL programming language that they're using for the rest of their robots, and there's actually Java 1.6 that was on the back end, so you could start doing some funkier things like embedding web servers and whatnot onto the actual robot to control it from a distance. But we'll get into this. We'll get into the robot that you see in my background over here a bit too. I'll slip that in since Steve mentioned it. And there'll be some math, there'll be some robots, there'll be a little bit of everything.
Cool.
All right. Everybody gather back to your computers, and we shall get on with our feature presentation. So today we have Dr. Nicholos Nadeau, who is a professional engineer and a member of I'm gonna just sort of, I'm translating, I believe, is the Order of Engineers of Quebec. He received his PhD from, let's see, is that École de Technologie Supérieure? I'm not very good with French, so. His research combined machine learning and collaborative robotics to develop safe robotic freehand medical ultrasound methods. Well, that sounds pretty fascinating right there. We might want to hear about that sometime. Nicholos is actively involved in the Montreal startup community and is a mentor at several accelerators, including Next AI, Techstars, Creative Destruction Lab, and Founder Fuel. So he is, and you are in Montreal right now, is that right?
Yeah, I'm an East Coaster.
Okay, yeah. So welcome. This is since we've started doing presentations online. It's been really cool to get people from literally all over the planet talking to us about robots, and it's wonderful to just expand our horizons like that. So thank you so much for joining us today, and I'm going to just hand you the ball. So please proceed.
Well, thank you very much, Steve, for inviting me here today. So hello, everyone. I'm Nicholos, based in Montreal, bit of a roboticist. Let's call myself a full stack hardware engineer in a lot of ways. So as Steve mentioned, right now I'm the CTO of Halodi Robotics, a Norwegian robotics company. So speaking of international, it's nice to bring, especially with the technology we have today, people from all around the world to work on a common passion. So that's what you see in the top left. We build about a 6 foot tall humanoid robot currently used in security guarding, some Industry 4.0 applications, and retail. We recently signed, I think at the beginning of this year, the world's largest order for humanoid robots, ADT Commercial, so the blue hexagon. They ordered hundreds of robots that they'll be deploying over the next year or two as security guards. Basically, can we help automate the dull and dangerous task of that 2 a.m. night shift that's just going up and down that dark hallway, not doing much. Otherwise, did my PhD at ETS, so École de Technologie Supérieure here in Montreal, on, as Steve mentioned, collaborative robots, applying a lot of the machine learning, robotics techniques, force control, and things like that to medical ultrasound. So really taking a health and safety approach. Ultrasound technicians and sonographers, they had a higher rate of carpal tunnel syndrome while performing their work from doing repetitive motions with the probe. And so can we help robots work alongside them and do that in a collaborative fashion, human-robot collaboration, to help reduce the occurrence of things like carpal tunnel syndrome? Brought some companies through accelerators in the venture capital world. One was a food robotics company using the universal robot arms. Can we automate the kitchen in a lot of ways? Doing these rote, dull tasks that we're having a lot of trouble with a human labor shortage right now. And then I spent a period of time actually as the head of engineering at Aeon 3D, an additive manufacturing, so high performance 3D printing company, where we're able to print very large, so about a meter tall by half meter by half meter print volumes of PEEK, PEC, and Ultim, mostly for the aerospace, medical, military markets. And we actually got the first parts on the moon and the space station built out of Ultim. So that was a lot of fun. And so today's talk, we could save for the discussions. I'll talk deeper about like Halodi or anything like that. But it's going to focus mostly on Pybotics, which is the software package in Python that I wrote back in the day. Steve asked me to talk a bit about that. We're going to dive into some of the ultrasound work, some force control, robot optimization, robot calibration. A lot of this actually stems from my original background was in mechanical engineering. So I started off as a mechanical engineer in the biomedical field, designing brain implants, brain imaging devices, things like that, and eventually got into surgical robots. And from there, I realized that accuracy, calibration, all those things were pretty important. So we'll be talking about Pybotics and calibration. We'll be going into impedance control calibration, some hardware in the loop stuff, especially seeing the projects you guys demonstrated today. You guys are really doing some really interesting things that are combining a bit of software, hardware, and working in unstructured environments like the human kitchen. And we'll get into some motion control optimization as well. So first up, Pybotics and calibration. So starting up, what's the difference between these two robots really, aside from the probably 100x price tag difference? On the left, we have the KUKA LBR Collabor robot. It was one of the first Collabor robots on the market, I think 10-ish years ago. On the right, we have a hobby robot. Really, the biggest difference comes in the joints. Each of the joints in the KUKA robot is a harmonic drive gearbox. I won't get into necessarily the details of that, but let's just say it's a very, very large torque ratio or drivetrain ratio between the input and the output stages. And this allows you to create very precise motions. Unfortunately, each of those gearboxes costs anywhere from $1,000 to $2,000, which makes it a very expensive robot, especially when you have 7 degrees of freedom on the left. Whereas the robot on the right, you have a lot of direct drive, and so you have a little bit of slop, a little bit of looseness, and it makes for much poorer in terms of precision. But if we have such a precise robot on the left, why do we still need to calibrate it? Well, a lot of people mix up these two terms. There's precision and there's accuracy. Precision is also known as repeatability. Robots are very precise out of the box, especially industrial robots. You can go back to the same position in space over and over and over again. With a high-end industrial robot, you'll probably hit it in the 1 to 10 micron accuracy range. But out of the box, a lot of these industrial robots are absolutely terrible at accuracy, anywhere from up to a centimeter to outside of your target position in space. And this really stems from the fact that robots work in joint space. So when you command a robot to go to the same location over and over again, it's essentially saving those joint encoder positions and just going to that very accurate joint space position. When you tell a robot to go to an arbitrary position in your XYZ Cartesian space, it has to really figure out where that is using things like forward and inverse kinematics. And you have all the little inaccuracies from machining, from assembly of the robot, up the kinematic chain that produces an inaccurate final positioning of the robot. And so where is accuracy important? Well, it really comes in when you're doing things like offline programming, which is more and more popular in the industrial space. You don't want to necessarily shut down your whole assembly line to program your robot for the next job, because time is money. And so instead, we simulate the robot work cells and production lines offline, able to do all the motion planning and everything ahead of time, and then deploy them onto the robot. So you have much more reduced downtime. And as a roboticist, you get to do all your programming while you're in your PJs at home. The unfortunate part is if your robot in simulation isn't the same model as your robot in the real world, it will lead to a lot of collisions and crashes. And so we want to make sure that the sim to real gap is minimized as much as possible. And so by calibrating the robots, we're able to more accurately transfer this offline plan to the real world robot and achieve the results we expect. This is also important when you're doing robot surgery. You don't want to have an oops when you're trying to drill into a subject's brain, do injections and things like that. And so this is an example of a surgical robot that I put together, actually using an industrial robot back in the day for small animal neurosurgery. We got accuracies down to about 5 microns, and this was the skull of, well, the 3D printed skull using the imaging data of a marmoset, which is about 2-3 centimeters wide. So you want to be pretty accurate when doing some of these surgeries. And so what are we actually doing when I say calibration? Well, we're correcting for the joint inaccuracies, the position inaccuracies, the distance inaccuracies along the kinematic chain. My favorite way of describing robots is modified Devenant-Hardenberg parameters. And so you have essentially 4 parameters per joint along the kinematic chain. And what you're trying to do is get the better value for those values in an iterative fashion, such that the transforms along the robot's kinematic chain is as accurate as possible and matches the real world robot. Most robots out of the box, the company will provide you what the nominal kinematic chain is supposed to be, and it's nice round numbers usually. When you start to do the calibration, you find out what the actual values are. And so why did I put together Pybotics? Well, back in PhD days, I realized that everything was a MATLAB toolbox in the end. I could go down a rabbit hole of why I do not enjoy MATLAB. And so I wanted to put together something that was in the Python ecosystem, which was much more open source, much more freely available to everyone outside of academia. And really be part of that open source movement of democratizing these tools. I also want to connect it to the ongoing work in the scientific compute and the ML ecosystem. So everything from scikit-learn to NumPy to SciPy and the TensorFlow PyTorch packages that were starting up 10-ish years ago. If we could vectorize our robots, we can then basically apply machine learning and optimization to them using these open source tools, which got me thinking. And so freely available, if any of you want to check it out later on, I have Jupyter notebooks and everything up and running for demos. It's actually been published, so there's open source publications as well talking about this, and a whole bunch of applications using this in the real world. Otherwise, the big focus of this package is really to do kinematics, dynamics, and calibration such that you're more easily able to do trajectory generation, some other robotics algorithms, and the AI ML attached to that. And so it's a bit heavy on the mathy side, but it's one of those fundamental tools that lets you really get started and then go on further to explore and optimize your application. So if we look at the calibration process as a whole, it's really just a simple 3-step process. There's not too much that's fancy about it. We start off by measuring a series of poses with the robot. So we try to collect a data set of joint configuration, so joint 1 through 6 or 7, depending on the type of robot you have, and what is the position in space. We then try to optimize the model by iteratively reducing and minimizing the errors between the calculated forward kinematics of the model and the actual Cartesian poses. And then with a second data set that we keep to the side, we validate the model. We want to make sure that when we do the optimization, it actually achieved what we expected to, and we actually got less error in our accuracy. And so what this looks like in the actual code is first we calculate the forward kinematics. I'm just going to minimize that. First, we calculate the forward kinematics and compute the expected Cartesian pose of the model given our joint angles. We calculate the errors between what the nominal model says is the position in space and what we actually measured. And then we update our model accordingly and we try to recalculate. And it's just a big cyclical loop until you get a better model and an error that passes a threshold that you set. In Pybotics, the way I set it up was I want to vectorize my robot. I want to represent the robot as a vector of floating point numbers, essentially, that we can minimize. And so the robot is modeled as a vector of your tool frame, your kinematic chain, your world frame. So your tool frame is essentially your transform from your last joint to your tool center point. So like what Greg was showing there with his big jaws of life claw there. it'd be the transform from the attachment point on the rest of the robot arm all the way to that, probably that last tip there, or maybe even the center of the gripper. Your kinematic chain is your modified Devon and Hardenberg parameters along the robot. So you have your alpha, your A, your theta, and your D, which represents your transforms along the robot arm. And then you have your world frame. And this is actually probably one of the most important frames on there. And it's really, where do you designate the origin of your robot space to the base of the robot? I got to, during my PhD, play with some really fancy tools, and I'm not going to lie, this was a lot of fun to play with a Faro ion laser tracker. This is essentially a measurement device that lets you measure any position in space using these, what they call SMR, so a spherical something magnetic retroreflectors, and it essentially lets you measure an accurate position space at plus or minus, I think, plus or minus 5 microns in a 50-meter sphere. So super accurate little R2D2 bot. And so we essentially attach the SMRs to the end of the robot and move the robot around and have this little R2D2 track the robot position in space and build up a data set of positions. And this is what the measurement process actually looks like. I attached a plate to the end of the robot with that SMR attached to it, have the robot essentially do a dance for hours upon hours upon hours. And like any good grad student, this was probably filmed at 3 a.m. as I was having the robot just do all-nighters of recording position after position. Especially I want to collect the best data possible. So doing it in the middle of the night when no one was around, less vibrations in the building and everything like that. And we eventually come to having a point cloud of positions in the robot's workspace that we can then optimize around. And essentially with Pybotics, I was able to make the whole optimization process going from an inaccurate robot to an accurate robot, just 29 lines of code here, importing your standard Python tools like Pandas and SciPy and scikit-learn. We're able to load a robot model from Pybotics, which represents the robot, represents that vectorized version of the robot and its kinematic chain, load our positions and joints from the CSV of the data we recorded. With scikit-learn, I like to split the data into a training set and a testing set, and then we optimize, and we essentially run, for the most part, just a least squares optimizer to minimize the model's errors with respect to what we measured in the real world. And out comes a calibrated robot that you're able to then load into other programs or anything like that, because it's just a vector, a matrix of positions and transformations along the kinematic chain. But this led me to realize that not everyone has access to $100,000 laser trackers by Faro, even though they're a lot of fun to play with. Accuracy is a fundamental requirement for a lot of robot applications, but it wasn't necessarily accessible. And so we developed a method to try and reduce the barrier to entry into calibration. And as such, using basically your standard mechanical engineering tooling balls and kinematic coupling, this whole setup here costs less than $1,000 compared to the $100,000 laser tracker robot. And so the tooling was composed of the calibration plate with large tooling spheres, trihedral coupling you see on the right. On the right, you see the coupling has a magnet embedded into it. So this helps us really stick on to the tooling balls as best as possible. And especially since this was a force-controlled robot, we're able to take advantage of that force control to, get a little more accurate coupling to the spheres. Everything was sourced by your standard online vendors, McMaster-Carr, etc. So nothing too custom, nothing too crazy. And prior to running this whole experiment, we did the laser tracker method in order to, compare the two methods with each other. And from a controls perspective, we really exploited the built-in real-time impedance control of the KUKA robot. So being that we can create a virtual spring damper system with the robot, we're able to get close enough to the sphere and then just let the magnetic force pull the robot that last little bit with a variable stiffness in order to make sure that we were fully coupled to the sphere as best as possible. And so it was a lot of fun because, once again, the robot out of the box is inaccurate. So we don't know where the sphere is we know approximately where it is, we get pretty close. But if I try to go in a full position control way straight to the sphere, I probably collide with the sphere over and over again, damaging the robot, damaging the sphere, and just messing up my tooling as a whole. And so by getting as close as possible with position control and then switching into an impedance control control paradigm, we're able to then snap and self-center onto the tooling sphere. And so this is what the process essentially looks like. Come in position control and you have a little snapping action. And then we're also able to just move around the sphere. So now that you've coupled to one sphere position, you're able to rotate around there. So you can maintain one virtual point in space, but collect many different joint configurations around this virtual point. And then since this was a 7 degree of freedom robot, we have a redundant axis. And so we're actually able to move the robot through the null space. So we're able to keep one position in real space and move the robot's body fully without moving the tool at the end, the tool position. And this was a lot of fun. So the way I logged the data was snapping to the spheres, waiting a little bit to let the torques and vibrations stabilize, and then record many positions and poses with keeping a constant final tool pose and moving the body through the null space, and then moving around and repeating that, collecting hundreds, if not thousands of poses. And so once again, this is the KUKA LBR, so 7 axes, and we could take advantage of the redundancy to move through the null space, keeping a final tool pose. Once again, using this data of positions in space with respect to joint configurations, going through a standard minimization process using Pybotics again. And so so this is a combination of the data from the laser method and the sphere method now. And out of the box, this really expensive, and back in the day, the KUKA LBR, I think was $200,000, something crazy like that. Out of the box, it's about 2.5 millimeters inaccurate in space. And so if you're paying that much money for a robot, you expect it to do better than 2.5 millimeters of inaccuracy. Using the laser method, we're able to get it down to about less than 0.9 millimeters absolute accuracy in the real space. And using the very cheap sphere method, it was actually pretty similar to the laser method. Not as good on average, but the max error achieved was comparable. So it was really nice being able to compare $1,000 tooling to $100,000 tooling and help democratize calibration to the masses. And so simple, low cost, robust. It was really nice because since everything's just steel, you could put into more rough environments compared to the very fragile R2D2 laser tracker. Because it's low cost, we can then maybe even equip every work cell in a factory or facility with this next to the robot, such that you can maybe every week or so, the robot could just turn to the left and do its own recalibration. And this was really taking advantage of the incoming trend of collaborative robots that we were seeing, and the more accessible force control and impedance control methods that were coming out. So we had robots running, robots being calibrated. How can we make this whole process more efficient? Essentially have the robots run themselves at a certain point. And so one thing I noticed in the whole machine learning and robot optimization workflow is we had to collect a lot of training data. We had to model everything, we had to make predictions or optimizations, and we had to update our model and repeat. In the typical approach, that involved a lot of CSV files and running things manually, collecting the data, copy and pasting things and moving things around. But I want to make this process a lot more optimized, especially if we want to make it more accessible to the real world. And so one of the things is robots have always been, up to a certain point, robots isolated. You program them with teach pendants or offline program things, you deploy it, and then they repeat the same thing over and over again. But how do we actually connect these robots as physical agents, essentially, to the software process? And it was really interesting because, like, for instance, the robot, the KUKA robot, was running a really old Java stack. I think it was Java 1.6 that they were based on, and all the data science and machine learning side of things is all in Python. And so how do we connect these two running systems in parallel? And so my best friend over the past little while has been gRPC. If you ever had the chance to play with gRPC to communicate things back and forth. It's a lot of fun. Available, open source, available in basically every programming language now. And this essentially lets you solve the communication issues between different systems. It lets you create a client-server model between the robot and the Python stack. So the robot is essentially a server that performs commands on queue, and your Python stack or your computer, your client, your tablet, whatever, is a client that connects to this arbitrary robot and says, please do this for me, please do that for me. And so being that the robot was a server in the eyes of the data models and the training algorithms, the function callbacks from optimization, like evaluate the next pose, evaluate, try this, try that, are just part of the loop. And you just call a function saying, robot, do this, collect the data back, and you could keep this in an optimized way running in situ. And so the return value from performing actions would be the robot sensor data for doing this calibration. And so once again, for those not familiar with gRPC, it's really nice because we get to define our communication framework and our service in a language neutral, what's called a proto file. And so we just say, for instance, that there's a robot service. It moves, it gets joints, and it returns a session result. And the session result is just filled with joint. It's just filled with the status, and then the joints we send to it is just an array of joints. This is language neutral. You run a few scripts, and gRPC will auto-generate all the communication code you need for you in Python and Java and JavaScript and Go and whatever language you want. So you sort of write once, deploy to many different applications, and you don't have to rewrite the same communication interface in every language or for every system that you want to work with. And so it's a lot of fun because it integrates nicely if you're into CI/CD and that whole software development lifecycle. It makes for very nice updates, nice sharing and submodulating between your different code stacks, and it makes the whole application much more efficient. And so this is what it looks like from the Python side. We just initiate a controller client, and we say where, what host and port we expect the server to be on, and connect. And then the robot is essentially just one function away from moving for us and collecting data for us from the Python code. And so for the actual training and the optimization steps, the robot is just a simple function provider. So we can just set it as the callback for our optimization function. And so this is an example using SciPy's optimization, where it asks for a callback function that it will evaluate at every session. And so every time instead of evaluating the function in software, we're evaluating a function in hardware. Essentially, the robot is the function. The robot will do something and submit its results back to the optimization loop. And so this gets even a lot more fun when you do funky things like poking with the robot. And I have some videos later. One thing I was exploring was, can we optimize around soft body contact? Can we optimize around having the robot poke humans, poke human tissue and things like that when performing ultrasound? But this was all built on the same premise: is can we have the Python data science stack say do something, essentially communicate over gRPC, have the robot move, send its sensor data back, collect the training, and just optimize this whole process so that I personally don't have to sit in a graduate student's office until 3 a.m. collecting data. The robot can handle itself and optimize itself. And so it creates a wonderful separation of concerns across the code base. So we can have our robot code base with the gRPC as the interface. We could have our Python code base with the gRPC interface. We could have the Faro Ion laser tractor with its own gRPC interface. And we could just sort of like what ROS provides, mix and match tools, but outside of the ROS ecosystem, making for a much lighter weight application. And so this is what the final application looked like when I was doing a lot of the calibration, was that the robot was a server, the Faro Ion was a server. And so the Python stack would just say, robot, go here, Faro Ion, measure there, collect data, thank you very much. Everybody go to your next position, and just loop and loop and loop like that. And so it's scalable across many robots, scalable across many different accessories like other measurement tools. And your client, your Python stack, doesn't need to know about robots. It doesn't need to know about laser trackers. It doesn't need to know about how they're implemented, what kind of code base they're running on. It's a black box server, essentially, that all it is I am sending you a series of joints that I want you to magically go to, and I'm expecting back in return your final position in space. Whatever happens in between, That's for you to take care of. And so from a hardware engineer perspective, this really reduces the time to deployment through the automation and a very well-defined interface between these systems.
Dr. Nadeau,
Yeah.
does it have any kind of self-correction? Let's say a servo loses power for some reason, or just slightly loses power. That's going to change its position. So
Yeah.
does it have any way to know that it goofed?
Yep. So the KUKA robot in particular was actually actively at about a kilohertz measuring input and output torques on both sides of the gearbox. And so if there was any difference between the two sensors, it goes into a full safety stop and sends you a lot of warnings and a lot of errors. The robot was actually, it was very well designed, the robot. It was very expensive, but it was very well designed. In terms of being redundant with safety, redundant in number of joints, and very, very good at failing gracefully, essentially, and being able to detect when things weren't kosher. Did that
Does
answer
it do any?
your question? Yeah.
Mostly, yeah.
All right, Mitch?
At my age, I worry about surgical robots.
Yeah, yeah.
Especially since I build robots, I know what kind of shit can happen.
Oh yeah, but look, I have the exact same feelings about half the mechanical things I see in life, and it's why I don't go on roller coasters for the most part. Mitch?
Can it do any troubleshooting on its own? You said that it sends a bunch of warnings and then just kind of locks up.
Yeah.
Are there, like certain ones that can't handle, need someone else to come back in and check out?
Yeah, so for the most part, you can self-correct most non-critical things. So if the one of the sensors on either side like just disappears fully because there's an electrical fault or pinched a cable and that connection broke, then it'll go into a full lockdown, which is actually very dangerous. And this was one of my big pushes in the day, was looking at safe robots. Is there are times when you want to fail gracefully. You basically always want to fail gracefully, but there's times when stopping is not the right solution, especially stopping when you potentially are clamping a human to a table. You want it to fail gracefully in some other way, not necessarily just going to a full lockdown mode. And the other problem with a full lockdown mode with this kind of robot is with the harmonic drives, you have upwards of 50, 100 to 1 gear ratios. It's very hard, if not impossible, to backdrive it. So when you're clamped, you're really clamped. And so that's can be seen, depending on the situation, as even more dangerous than potentially, maybe even continue with the motion or doing some other motion in a different direction. So that actually was probably one of the biggest blockers to making the system fully intrinsically safe, at the very least, is the fact that when you get into that really bad safety situation, it goes into a full clamping lockdown. And it's to be said, any robot with high gear ratios can be seen as not necessarily intrinsically safe because of the lack of backdrivability and the high reflected inertia in your gearbox. All that energy that's stored in the gearbox that's moving, if it collides with something, that energy has to go somewhere. And let's just hope it's not a human body on the other end of that arm. Otherwise, that's where, like, if I take a Halodi Robotics, for example, with the humanoid form factor, all our joints are basically quasi-direct drive, using capstan rope pulley systems inside with very, very low near unity ratios between the two. So everything's back drivable, everything's fully compliant. And so if the robot hits you at full speed, it's like a human arm hitting you. You're just going to reflect the force back through the robot body instead of it going through you. But in order to do that, you need motors that have very high torque to weight ratios to make that possible. So each of our motors have significantly more torque than a KUKA motor does. KUKA gets to make much more or use much lighter weight, smaller motors and just slap on a big old gearbox on the end of it and call it a day. So it's trade-offs. They'll have a more precise robot because of that high gear ratio, but it'll be more dangerous in a lot of situations. So little trade-offs here and there. It's never easy. And so eventually we got to, with this whole robot in the loop setup, we got to optimize the motion control around physical human robot interaction. And so I was performing ultrasound on lower limbs, looking at stenosis. So that's the cardiovascular disease, mostly found in the lower limb region. Sonographers, once again, carpal tunnel and all those types of things we want to look at. We also want to look at, can we use ultrasound beam that's very safe, very effective, and very low cost as an imaging, a medical imaging technique? Can we use 2D ultrasound and using robot control, move it along the human leg in a very controlled trajectory, turning that into 3D ultrasound by composing and synthesizing all your 2D slices? And if you're able to have an accurate robot that's able to repeat its motion over and over again along the same trajectory, you can essentially turn it into 4D ultrasound, where you take that 3D image and apply that time dimension to see how things are changing over time. And so pure motion control, mostly insufficient for most of these types of tasks. And so we had to create a control paradigm of how do we move accurately through defined trajectories while also keeping your ultrasound probe, against the changing stiffness and the compliant, unstructured human body without hurting the person. And so you have this multimodal controls approach of hybrid force impedance control and hybrid force position control. And so this was the first time I tried to, so this is a model human limb. It's actually autonomically correct. There is a bone structure in there. There are skin layers and muscle layers in there. It's really to replicate the human body as best as possible. And if you apply just, out of the box motion control or force control to try and move on it, you get this very bouncy motion because the robot's trying to, in its control loop, maintain a force, bounces off, tries to maintain that force, and you just bounce along. And so this is a safety concern, trajectory planning as a whole, safety concern, because we want to make sure that we follow the trajectory that we want without clamping the person, without injuring the person. We don't want to overshoot our forces when trying to clamp down. And so what I want to look at is, can we have sort of like a hardware in the loop tuning framework to really optimize our force control for the different regions of the human body? And so same idea as before, have the robot in the loop. In this experiment, I used differential evolution, which is a method inspired by biology of trying different things and then merging the results into a population of candidate solutions that create new solutions through recombination, allowing you to really explore all the possible models for robot control. And so this is especially important for robotics because there's no real single solution, and the overall solution space is assumed to be pretty noisy and not guaranteed to be differentiable, which is super important for other techniques like your standard least squares. And so having the robot in loops, I was able to basically have it self-tune along this human leg, eventually finding a model that worked good enough that we're able to then transfer off into other humans and things like that. And it's only after about, I think it was like 700 or so sessions that we're able to converge on a pretty strong solution. And this 700 sessions sounds like a lot, but when the robot's doing everything itself, it's only like 20 minutes for it to figure out what the best control method is to move along the human body. And so eventually we were able to do smooth motion along human limbs with an error of only about 0.5 newtons throughout its entire motion compared to what we want to press. And so one important part of doing medical ultrasound is not necessarily maintaining a given position, but you want to maintain a given force along the human body as the human leg will compress in different ways in different regions. And so a lot of fun, a lot of people questioning what I was doing in the lab when they would walk by the window and see a human leg on the table and a robot poking along it. And so total optimization time was measured in minutes, being that everything was just automated in a loop. And this, even though, this probably won't be used in the real world in medicine for a long time, the same idea of having hardware in the loop and self-optimization can be used in everything from the calibration we saw before to the robots you guys were looking at for opening refrigerator doors to a little bit of anything. Anytime you want the robot to do, it's essentially a cheap form of reinforcement learning at a certain point, but using instead of a black box neural network that no one understands, you're using the actual robot parameters that you program.
How do you compensate for the human factor? Like here you're using a false leg that's going to be in the exact same position every time. But like I know when I'm laying on an examine table, if I even just hiccup, I've changed my position a little. So how can the robot compensate for the human?
So for this particular experiment, I'm going to use the very academic answer of it was out of scope for that particular experiment. There was some follow-on stuff that started using computer vision. So you have a separate camera in the OR space that tracks the leg, and then you're able to essentially match and coordinate the robot to the moving frame of the patient. The patient, as long as the patient doesn't move too fast, you're able to track where the patient's leg is going. And the robot, when doing these motions, is always seeing a frozen frame of reference because you're essentially shifting your frame with respect to the human.
Okay, that's tracking dancing motion and stuff.
Yeah.
Okay.
James, I think your hand is up.
Yeah, so I'm curious, when you say, quote, hardware in the loop, I'm just a little bit curious about what exactly that is. Are you talking about an embedded system or an FPGA or a...
I'm saying the whole robot.
Huh?
Yeah, so the whole robot, so basically taking the robot to essentially, I hate using like learn, but it's essentially self-learning its optimal model by repeatedly doing things. So this is the actual robot, the robot's full controller, which in the case of the KUKA is, I think it's just an embedded Windows PC is the robot controller that KUKA provides. That real-time control is embedded in or communicating with the Python stack in order to optimize itself. And through repeated iterations as it tries new things, we're actually updating the robot's controller.
Yeah, I understand now. Thank you. I was just curious how fast that loop was. And so what you're saying is
it could go as fast as it could go as fast as the robot communicates. And so the KUKA in this particular instance had a control loop rate accessible to the outside of about 1 kilohertz. Now robots don't move in the physical space, so the actual blocker is physical movement. The slowest part is the robot trying out a new iteration. So this is what, a couple 3 to 5 seconds, let's say, of motion. So if this was an iteration, it would try it, do 3 to 5 seconds, and then pump back the force data and all the other data that we collected with the robot's onboard sensors back to the Python stack. The Python does its magic and calculates what the next attempt should look like, pushes that back to the robot, and the robot tries again. So what you're seeing right here actually is the slowest part of this entire loop, the fact that you actually have to physically try it. There is a lot of work being done these days with NVIDIA, with their Omniverse stuff, where a lot of people are starting to use the game engines like Unity or Unreal. There's also Mojoku. These are all simulation stacks that are trying their best to simulate the real world as best as possible, and that you can actually parallelize. All you're limited by is how many GPUs and NVIDIA graphics cards you have, and you could simulate things like this in parallel 1,000-fold. But at the end of the day, at one point or another, you have to try it in the real world.
Simulations are doomed to succeed.
Well, yes and no. I'm a big believer in simulation for getting a starting point. As much as I try to push my companies to simulate more and more, you always have to deploy to a real world. And so my dream is to have simulations running in parallel of a robot gym. I love the idea of like having an aircraft hangar with drywall and 2x4s everywhere, and having robots just living their best lives, living like the Truman Show in these worlds where you're deploying the latest models, the latest code, and you're getting that physical feedback while your simulators are making sure it's essentially it's a low pass filter in a way.
So the systems that I've seen where they have success, they do like 1,000 simulations and then they run out and try it on the real thing, and then they correct everything back to what the real world response actually was, and then they do go off and do another 1,000 simulations, and then you know, or some number. I'm not saying 1,000 exactly, but that's the general idea. So, but the point is to keep coming back and connecting it back to the real world every so often to make sure that your simulation doesn't just go off into fantasy land.
Yeah, exactly. And your simulation doesn't go off into fantasy land, and that your simulator is able to capture the really bad code. And so, for instance, if your controls team pushes new code that makes your robot, like with my humanoid robot here, if a junior developer comes in and tries new control code and pushes something that makes the robot faceplant every 5 seconds, that would be very expensive to repair. So your simulator is usually able to capture that really bad stuff. And then once you have good enough in simulation, you deploy it to the real world to fine tune it. So yeah, that's the gist of what I have for you today. Thank you very much, everyone, for having me here. Thank you very much, Steve, for reaching out, and chat as much as you want.
I have a few questions if you have time.
I have time.
Awesome. The specific Faro unit that you were using, is that, I don't see that on their webpage. I was just curious.
This was 10 years ago. That's a Faro Ion back in the day. I think it's the Vantage they call it now. But
yeah, the price isn't 100,000 anymore.
no.
Sadly.
My professor back in the day was very, very cautious of letting grad students play with that at any point.
Yeah, those are unfortunately super, super expensive. Love the idea that you had with the magnetics on the balls for the lower cost calibration. I'm curious, all of the, for example, on the optical breadboard there, you had 3 balls. They're all the same Z height, I would call it.
Yeah.
Did you not need to have one at a different height or try some things that weren't in that one plane in order to get a good calibration?
It could have been a different height, but so a sphere is just a point in space. 3 spheres, 3 points makes a plane. And so it doesn't matter what height a third one of it would point, 2 of them, if the 2 were different, they all make a plane in space.
Yeah, sorry, I didn't ask my question very well. Okay, so you got your 3 balls, they're all making a plane, you do the calibration, and now you tell it to go to a position that's not on that plane. In other words, do you not have problems then when you exit the plane?
You're saying the calibration would be overfit to just the plane where I'm working in and calibrating?
That's the concern I have. So I'm asking whether or not you had that problem or you didn't have.
No. So the robot was calibrated with what you see here, and then if I go back, this was the same data set. This is all part of the multi-stages of the same overall experiment. This is the full workspace of the robot. So even though we calibrated in just a smaller subset area, it was good enough for the global workspace of the robot.
Oh, that's very encouraging. That's great.
Yeah. So as long as the key was getting as many joint configurations as wide and variant as possible. So you want your robot's body to move
by rotating. Yeah.
Exactly.
Yeah. So that was really the key point, is having that. And I'm assuming that that's a metal fixture, and then you have a magnet up behind it somewhere, so the magnetic field is coming down through the magnet.
Yeah.
Through the metal fixture, or was that actually a machined magnet?
No, that is off the shelf. So everything you see here, except the silver plate on the right, which is just 6061 aluminum with a bunch of holes, and everything else was off the shelf actually. Yeah, there's only one custom part there and a bunch of screws. And basically we also don't care the accuracy of the 3 balls on the left of where they're placed. We just care to know what their relative position to each other is. Because when we're doing the actual optimization, where the error we're measuring is not the absolute position of the balls, it's the error of the distance or the vector between the balls, between each ball with each other. So 1 with respect to 2, 1 with respect to 3, 2 with respect to 3. And so this also brings down the cost really low, because we could put these balls in whichever position orientation we want. We just got to measure them with respect to each other, which is cheap, to do overall. If you have a friend with a CMM, you could do that in 5 minutes, or there's other methods of measuring balls with respect to each other.
What's the what do you know, or do you remember right off the top of your head what the source was for those off-the-shelf parts, the balls, the mounts?
Yeah, I think the company was like machineballs.com or precisionballs.com. Let me just quickly. Yeah, I'm pretty sure it's like precisionballs.com, but McMaster-Carr has them. Any old McMaster-Carr or Granger, most of those sites will have similar, if not equivalent.
Is there a particular phrase or word or whatever that you would?
It's
search
the
for?
standard. It's kinematic coupling, so that's the standard. The thing on the right, the little nest with it's basically a small cylinder with 3 perpendicular cuts into it, such that it always snaps to a sphere in the same exact location. That's called a kinematic coupling. The balls are just tooling balls. That's the usual search phrase for them. You might often find kinematic couplings with a ball and nest as a set, but that's really it. It's not too bad. Precision ball.
Oh, I think I finally found it. Yeah, that was difficult to.
Yeah, it's precisionballs.com. That's the site I got it off of.
So I lost something in that part of your description. You're moving the coupler to a position that you think is very close to the ball.
Mm-hmm.
And then you're allowing the magnet to draw the coupler to the ball. And then what are you measuring to know like how far off you are, or what the final joint angles are at that point?
Yeah. So what you see on the left here is we first in position space just get close to the ball. So ahead of time, I would have jogged the robot manually with the teach pin in a bit to know approximately where each ball was, and then with with offline programmer or whatnot, those are my waypoints essentially for getting as close to balls as possible. There's a sort of moment that just sort of jumps over on the left image. I'm actually switching control modes in the robot and going from position control to a force control method. I'm saying in the robot's controller, I don't want you to maintain a position space. I want you to maintain a virtual spring in space, if you will.
Okay.
And that center point of the spring is approximately where the center of the ball is, such that the robot will get pulled the magnetic force will pull the robot's tool center point down towards the ball and maintain a virtual spring damper there. Then I'm looking at, so this robot is just equipped with force sensors everywhere. I'm actually looking at the torques at each of the joint. I'm waiting for the vibrations to dwindle off, which took half a second or so before then recording, okay, what is my current joint angles? And I'm at ball position 1. And so ball position 1 for me was origin, so 0, 0, 0. And then I move through joint space, but I'm always at ball position origin. My tool center point is always at technically 0, 0, 0. And this lets me essentially move through all of my joint space, hundreds, thousands of joint configurations, but I'm always at the same position at the tool tip.
So each joint has, you mentioned earlier, force sensors going in and out of that joint. Yeah. And then they each have rotational position sensors.
Yeah, exactly. So all industrial robots have a full access to joint encoders. And so you have very accurate joint positions. All collaborative robots, and probably most robots built in the past 10 years, have also access to force or at least the torque data of each of the joints. And this lets you do things like force control. It lets you do things like record the torques along each of the joints to look for contact and things like that. And so by the fact that I'm able to snap, I can detect that spike of force and say, okay, I'm now in contact with the tooling sphere. Because it's a kinematic coupling, I know that the contact with the sphere is exact. And once I've snapped, I then start recording my joint angles. So I'll record joint angle 1, good, move to a new position, joint angle 2, and so essentially I build a CSV file of the row is 7 joint angles and then position in space. 7 joint angles, and keep moving and collect and build that out. And then I move to the next sphere and repeat the whole process.
And then I assume, I mean, it doesn't look like these arms would have an issue with it, but deflection between joints, is that not an issue?
So, you've stumbled on this. One of the skeletons in the closet of calibration is we actually ignore that completely. So, industrial robots like this, the flexion, the friction of the joints, the flexion, the effects of temperature, all that type of stuff, technically has an effect. They are built strong enough, robust enough. This is all cast aluminum, that it's a very, very small error that occurs. And so you have in calibration essentially 3 levels of calibration. You have level 1 calibration is just your joint mastering, finding your 0 of your joint. And most people do that as part of regular usage anyways. What we're doing here is known as level 2 calibration. We're actually looking at the static errors of the kinematic chain, the little offsets and things like that. Then if you want to be really fancy and do a whole PhD on one topic, you can do level 3 calibration, and that's where you take into account your dynamic errors, gravity, your flexion, your torque and your friction of the joint, the temperature in the room, all these things. To be honest, you might get another 10 microns of accuracy. It's really not that much, unless you're working in environments where your temperature change is very significant, like you're going in and out of a fridge or something, or in an oven. You won't see much gain for the amount of work that's required for level 3 calibration.
Can I ask a question?
Oh, go ahead.
Being really old school, how does it tell on the round ball exactly what point on the ball is the center of that tool?
Yeah.
Because you're dealing with what looks to me like a big round ball and a great big sensor, and I don't see where the precision comes in.
Yeah, so the ball, being that the ball is a perfect sphere, if you will, it's a machine tool sphere that I think it's accurate in terms of like mechanical engineering, like your spherical roundout to, I think a 0.00001 inches or whatever. It's a very, very accurate ball. And your kinematic coupling, because it's 3 perpendicular faces that snap onto it, if you rotate around a perfect sphere, you're always maintaining a virtual center point that's the same.
Right.
And so we're essentially rotating around the exact same virtual center point. So as long as we are in full contact with the sphere, and that's what the magnet is for, essentially, is to always maintain that contact, we are always at the same point in space while being able to change our angle around the sphere.
You're using the center of the sphere as the point of contact.
Exactly. Okay. So our TCP, if you will, is the center of the sphere.
Just like gravity. Okay.
Yeah.
So I'm curious about the magnet again. Sorry. Is the
it's a strong magnet.
But is that gray thing with the shape of the ball milled into it, is that itself a magnet, or is there a magnet behind it?
So the let's call it the triangular trunk is just steel. The ball itself is steel. No magnets involved there. The grayish cylinder with the sort of rectangular cut is exactly that, a gray cylinder with rectangular cuts, and it has 3 machined faces that are perpendicular to each other. In the center of that, so not seen there, so concentric to the outside cylinder, in the center of that is a threaded, just a threaded through hole with a threaded magnet that goes into there. And so you're able to swap out magnets, change the force by swapping out magnets, if you will. Also able to change the position of the magnet. So if you want to, maintain the same magnet but bring it a little closer to get a little more magnetic force, you're able to do that as well. But
is there a
particular
phrase for finding that? I'm having a hard time finding that in the
I have the catalog open on my left here. I'm going to quickly look. If you want to ask, if anyone has any other questions, I'm just going to look on the left for exactly what I got.
Looks like you can see the magnet there in the FT.
Yeah, it's right under, exactly. It's right under the FT. And I'm looking at the website right now. The website has not changed at all in the 10 years since I did this.
That's nice. Nothing like consistency.
Yeah.
But while you're looking for that, I'm curious if you did any angular validation on the robot, or if that was just done by the manufacturer, the stage 1 calibration you were talking about.
Yeah, so stage level 1 calibration, it's done by the manufacturer. It's done actually not every time you start up this robot, but every time you move the robot, you're supposed to go through that as a mastering process, they call it. And just basically you wave the robot between your hard stops and your 0 point of the encoder, and you're just basically calibrating where your encoder is. It's like the cheapo calibration method. It makes sure that your joint encoders are correct, and you'll get to pretty much the approximate right location, but it won't get you too far. So James, to answer, I think they call it magnetically preloaded kinematic couplings. I'm going to copy the link and paste it in the chat. That looks like it. So it's just a rare earth magnet with a thread around it that you're able to shove into kinematic couplings.
Excellent. Thank you so much for sharing that.
Yeah, they are very strong magnets. So it's a word of warning. Be careful.
Don't put your hand in there to guide the robot arm down.
Oh no, you can put your hand in there. Just don't have like anything else between. Don't have your hand between anything else potentially.
Oh, I should probably stay away from it since I have a pacemaker.
Yeah, that shouldn't be so bad.
So I'm curious about the need for force feedback. I'm wondering about the possibility of either disabling the drive and back driving the robot to move it around, and then just using the joint sensors, which, of course would require a little bit more manual intervention. But the force sensing part is really difficult, and most of us are not going to be building KUKA level arms. But the point anyway is being able to just get it into some position and have the joint sensors read out where the robot thinks that joint is.
Exactly.
At all of those different positions.
So there was another extension of this work that I did that we essentially did exactly what you said, turn everything off essentially, and just hand guide the robot to position, use the magnet, snap the magnet plate on there, just like hit record, and just manually move the robot around in whatever infinity number of positions we wanted to get it into. And that was good enough. That is perfectly doable. Otherwise, you only need one axis of force. So if you want to just slap on, you SparkFun even sells little attachments for like the end of something that just measures force in one direction. That's all you really need to do that final snapping.
Just the force in and out of the ball.
Exactly, your Z-axis force if you're looking from like the tools magnet point. Well, if that's questions, thank you very much everyone for having me here today. You could contact me over here.
Available anywhere?
Yeah, all the software is available in my GitHub repo, and Pybotics with all the the examples, codes, Jupyter notebooks, and how to use it and all that is available on the repository as well.
Any chance you could paste that into the chat to save us having to type it out madly at high speed here?
Here we go. So there's that.
Yes.
Awesome. Thank you so much. This is literally the most amazing talk I've seen on Seattle Robotics Society, and I'm even including mine.
Oh, I appreciate it a lot.
Thank you. Thank you so much.
No, thank you
Nicholas,
very much, Steve, for having me. And it was
yeah,
great chatting with all of you.
Is this presentation by chance on that at that link or available online?
I'll export it and I'll make it available. I'll shoot you an email, Steve, after this, and we'll set it up somewhere.
Okay, that would be awesome. Thank you so much.
No problem.
All right. Let's see.
All right. I'm going to jump off now. Thank you very much, everyone. Have yourselves a great rest of the day.
Thank you again.
Yes. Let me let's see. There we go. That. And all right.
So whoever managed to pull him in, I just want to say thank you to them as well.
So it was another presenter that Robert Kellogg found. I mean, I think Robert, that's all he does all day long is he just looks for, he just scours the internet. He's just he's found some. I mean, I'm really impressed. He's just found all kinds of amazing presenters. I mean, we've had some great presentations, and so I have a very, very large list to work with. So I don't get a lot of times. I probably get maybe 1 in 10 generally will respond, but sometimes I just have to be persistent, hit them up a couple of times, and then sometimes they'll go, oh, maybe this guy is actually serious, And I think all these folks enjoy presenting to us because you guys you're a great crowd, You don't boo them, you don't hiss them, you don't throw tomatoes or anything. I mean, it's awesome.
That's what's
okay. Well, oh, there we go. Hey, it finally came up. Okay, so it just took a really long. It took about 30 seconds for that to come up there. So and ignore the before break review because I didn't get to this before we took our break. But as you know, every same Zoom link next month. Do not know for sure again about in-person meetings. But I know for some of you that's not even an option, even if we did it. So, but expect there to always be a Zoom meeting available. So, so please join us next time. I will get the video recording for this meeting up on the website here sometime this week. This is coming. We're getting down to the wire for moving here. So it's like we're just madly packing, throwing stuff in boxes, throwing stuff away, things like that. So. Any of you that have ever been through the process, it can be pretty all consuming. So, let's see, well, you can see there, you can send me meeting feedback if you like, and any, throw stuff in the chat, that, you want to be captured. Looks like there's lots of good stuff. I will post that along with the meeting video and the meeting slides then. So if there's anything in there that you wanted to go back or, any information, you don't have to write any of that stuff down. You can just go get it off the meeting info. But with that, yes.
Is your new house bigger than your old house was?
New house bigger. Yeah, that's funny. Actually, it's a little bit smaller. It's a little bit smaller. So, so we have been doing a lot of downsizing. So,
well, whatever. All the times I've moved, I found out that I'm going from a smaller house to a bigger house. I can never fit all the stuff into the new house.
Yeah. Well, I was kind of expecting that too. That actually kind of happened because the house we moved out of was actually smaller than this house that we're in now, and we still had to get rid of a lot of stuff, and it's like it all felt like it barely fit. So I don't understand the physics of what actually happened there, but I'm thinking that that's some kind of magical thing that afflicts you when you move. You know, you actually need more space after you move than you did before you move. So anyway, maybe somebody can explain that. Maybe somebody can find a presenter that can explain what's actually going on there. You know, that sounds like the something is like stuff is appearing out of fourth dimension.
Tetris. It has to do with Tetris and how well you can play Tetris.
Okay. Yeah, that makes sense. That makes sense.
So basically, what you want to do is just sit there and play Tetris, and then when your wife asks you for help packing things, just say, "Well, honey, I'm practicing for the unpacking process into the new house." That'll go over, right?
Oh yeah. That'll. Yeah, that's a lead balloon, all right.
Well, speaking as a wife, I say you better run if you try that.
Yeah. Well, I've learned, I've been married long enough to learn there's all kinds of things that I don't say and I don't suggest and I don't comment on. Just, okay, honey, I'll take care of that. Okay, with that, I'm going to go ahead and stop recording here. Thank you all for being here. This has been fun, as always.